Let's follow the buckling analysis of a beam based on the energy requirement. So as I already described to you just a minute ago, that the point when bifurcation buckling occurs, the membrane strain energy has to be converted into the bending strain energy. So for a beam, let's look at this particular problem and then go about defining the membrane strain energy and the bending strain energy and see how we can get to the buckling requirement or the buckling load. Here you can see that there is a beam over here, and it is under a pre-tension load given by load P. This can be because of some temperature which was applied, or some kind of clamp position, or some pre-stretching that was applied to this membrane, or this for this beam. So it's a tension load. It is simply fixed on one end and it is rolling on the other side. So under a certain load, when it bends, it would be able also to move towards this direction. You have an out-of-plane displacement under a load Q, which is given as a simply supported load. This load seems to be of a sinusoidal fashion, but we'll come to that in a bit. Now, under the certain load, there is a differential length dx, which is undergoing some change to the length ds, and this can be related by the relation given to you on the right-hand side. I'm not going to go through the details of this. This is something you already have done through buckling, but in the course, for example, but you can also find this in many reference books for buckling analysis. Let's get straight to the energy-based problem that we want to derive here. For lateral displacement, which is given as v, which is a function of x along the length, then the strain energy in bending, so I can write here bending strain energy, is given as ub, can be given by the standard expression in terms of the curvature. This bending strain energy is written as an integral over the length, of course, because we are considering the beam, so we are considering length 0 to L, times the bending stiffness, which is given as E times I, which is the modulus and the moment of inertia for the beam, multiplied by the curvature. So the curvature is given as a second derivative with respect to x of v squared times dx. So that is the definition of the strain energy in bending. So just as a side note, you have V, you have V dashed equal to dou V dou x, and V double dashed is equal to dou square V dou dx square. Now let's say that this displacement is going to occur without any axial displacement. It happens exactly, it stretches, so the beam is allowed to, is fixed on both sides. Then you have the differential dx changing into a new differential length ds, and the approximation is already given to you before. So the axial membrane strain for this case in the bar. So now we can define something called the membrane strain. So change color because it's all for membrane. The membrane strain in the bar, given as epsilon m, can then be written as the new length ds minus the reference length dx by the reference length, so change in length by unit length, which can be given as now ds dx minus 1. So you can write it simply as 1 plus half of v dash x square minus 1, which is equal to half of v dash x square. Now, this is the description for the membrane strain. And of course, if you remember, then the green strain will also result in the same relation, which we have described before. Now, during a small lateral displacement, the axial force P will always remain to be constant. So if we want to, under the certain load Q, we don't want it to compress or stretch from its clamp position, then of course you will have P remaining essentially constant. As each elemental length dx is going to lengthen by means of this membrane strain, then a certain amount of work is done by this force P, which is stored in the form of the internal energy or the strain energy in the system in the form of membrane strain energy. So the membrane strain energy is given as Um, can be written as the integral of, over the length 0 to L, of the load P, which is doing some work when the differential length dx is going to lengthen to ds by means of the membrane strain epsilon m. So if I just substitute all the terms that I already know, I will get the membrane strain to be equal to half integral of 0 to L P v dash x square dx. Now, of course, we need to assume some kind of a relation or geometric description of the displacement that is occurring. So if we assume the displacement V, V to be equal to a maximum displacement at the center with the sinusoidal function pi x by L, then by substituting this into UB and UM, we will get pi 4E I by 4L cubed times the central deflection square, and the membrane strain energy to be pi square P by 4L Vc square. Now, in the same way, if the lateral load is also a half sine wave, Q is equal to a maximum load at the center QC times sine of pi x by L, then the total potential energy, so the total potential energy of the system will be given as the bending strain energy plus the membrane strain energy minus the work done on the system. Of course, here the work done on the system will be then given as integral 0 to L Q, which is the load which is acting, times V dx. And this can then be written as, you have your sine functions for both of them. If you solve them, you will get, and integrate them over the length L from 0 to L, you will get QCL by 2 times the maximum displacement in the center, which is VC. Now, for equilibrium, we can substitute the UB and the UM in these relations. So for equilibrium, you will have the change in the potential energy with the lateral displacement V is going to be equal to 0. So I have to differentiate the total potential energy by means of the degree of freedom that I'm working on, from which after solving it, I will be able to get the maximum displacement VC to be defined as QCL by 2 times K plus KG. And if I write these terms out, then K would be equal to pi square EI by 2L cubed, and the geometric stiffness would be given as pi square P by 2L. So you can see it comes directly from here, which is just being differentiated by these terms over here to be solved for VC. When you add them up and you make it equal to 0, of course, your work done is also included. So buckling is going to occur when P is such that the displacement VC can be non-zero while the load QC is 0. Right? This follows the definition that we have already introduced in the previous description for buckling. So we can have a state where the QC or the PC load in this graph here does not change. So that remains 0, but at the same time, the displacement can occur. So this is the condition of bifurcation buckling that has been described by means of the energy principle. So now, if I take that assumption in mind and I say, okay, when QC is 0, VC can be non-zero, then in that case, I should be able to reduce the flexural stiffness to 0 when there is a certain load P, which is a critical load. Now it might seem confusing, so I should write this down. So let's say we have this equation over here where we can say that, well, let's just repeat this equation here. Let's just write the equation of VC. Therefore, VC is equal to QCL by 2 times K plus KG. Now we can write K plus KG times VC is equal to QCL by 2. Now for buckling condition, for buckling to occur, for a load QC to be 0, VC does not have to be 0. So in order to describe that, we can write this equation as K plus KG VC is equal to 0, which means if VC cannot be 0, then K plus KG must equal to 0, which means now the effective flexural stiffness has to be reduced. Now, so that K plus KG is equal to 0, the load P that is applied, not QC, but the load P should be equal to a certain critical load, so that if QC is 0, we still have a certain displacement VC. In order to get this, we can solve the equation K plus KG is equal to 0. We already have the relations for K and KG described before, so we have pi to the power 4 EI by 2L cubed would be equal to, added with pi square P by 2L would be equal to 0. Therefore, we can say that P is equal to minus, of course you can get rid of the terms over here, this will also come pi square. So P would be equal to minus pi square EI by L square. In this case, we must consider that this problem was applied to a perfect column under a perfectly applied load at its neutral axis. So if you look at this problem again, you can see that we assume that there is a column which was applied with a certain load P and with a load Q, which is acting perfectly around the system. However, in reality, this does not happen much. Now, if this is a perfect problem, so the load is acting at the neutral axis and the column that is being machined is exactly straight and the way it has to be, then there is no coupling between the membrane and the bending stresses. And then this situation becomes valid. However, generally there is always a certain initial imperfection which might be designed in the form of an initial curvature, or the load that is applied is slightly eccentric than the way it has to be, then the computed buckling load becomes inaccurate. So for a perfect problem, let's say the eccentricity is E, any kind of eccentricity. When E is 0, then the buckling load can be calculated in this way. However, as soon as the E increases, the membrane and the bending deformations become coupled. And for most practical problems, the buckling, for whichever buckling will appear, the membrane and the bending actions are always going to be coupled. So the linear bifurcation analysis is a serious setback to finding out an actual collapse load or an actual limit load. So nonlinear analysis therefore becomes more appropriate, so that the coupling of both the membrane and the bending energies and stiffness can be taken into account from the very beginning.